NENOMATICA, where mathematics meets YouTube excellence. Here is our reference example statement, shown exactly as a bold, orange formula. We'll come back to it after we build the rulebook. Rule 1. Strict less than with an integer bound. If the floor of x is less than n, then x itself must be less than n. Rule 2. Less than or equal to. If the floor of x is at most n, then x is strictly less than n plus 1. Rule 3. Strictly greater than. If the floor of x is greater than n, then x is at least n plus 1. Rule 4. Greater than or equal to. If the floor of x is at least n, then x starts at n. Rule 5. Handle coefficients in front of the floor. Isolate the floor first, then use the previous rules. If the threshold is not an integer, round up with the ceiling. Rule 6. Compound interval for the floor. Combine the lower bound and the upper bound results. Quick challenge. Predict the next step before it appears. Suppose 3 is less than or equal to the floor of x, which is less than or equal to 5. What interval for x do we get? We'll apply the compound rule. First, from floor of x greater than or equal to 3, we get x greater than or equal to 3. Next, from floor of x less than or equal to 5, we get x strictly less than 6. Finally, intersect the two to obtain the solution interval. One more mini example with a coefficient, 2 times the floor of x, at least 7. Isolate the floor, then apply the ceiling. We find x at least 4. Let's summarize the key ideas, then you can try a few on your own. Remember, strict versus non-strict inequalities shift the bound by 1 when moving from the floor to x. Compound ranges intersect lower and upper results. Next, explore the fractional part function for deeper insight. We will solve the inequality involving the fractional part of x, curly bracket x, squared minus 5 over 6 times curly bracket x, plus 1 over 6 less than 0. We will follow a clean, step-by-step algorithm and keep all math in bold on screen. First, show the word example. Then display the problem in bold orange. Step 1. Substitution. We replace the fractional part with a simpler variable y. This reduces visual clutter and lets us treat the expression like a standard quadratic in y. Show the step title. Now write the original inequality and the substituted version. Step 2. Clear the fractions. We multiply every term by 6. 6 is positive, so the direction of the inequality does not change. Show the step title. Now write the simplified inequality. Step 3. Solve the quadratic inequality. We can factor or use the quadratic formula to find the zeros. Show the step title. Factor the quadratic. Identify the roots 1/3 and 1/2. Since the parabola opens upward, the expression is negative between the roots, so y is between 1/3 and 1/2. We will also visualize this on a number line from 0 to 1. Step 4. Reverse substitution. We replace y with the original fractional part curly bracket x. Show the step title. Then write the inequality with the fractional part. Step 5. Solve for the general range of x. By definition of the fractional part, x equals k plus curly bracket x, where k is any integer. Show the step title. Add k to every part to get the general solution set. Step 6. State the final solution set. We gather all such intervals over every integer k. Show the step title. Then show the solution in green. Let's summarize what we did. We substituted the fractional part with y, cleared fractions, solved the quadratic inequality to get 1/3 less than y less than 1/2, substituted back curly bracket x, and finally used x equals k plus curly bracket x to express the full solution over all integers k. Example. We will solve the inequality 10 to the floor of x is less than 0.001, following the exact algorithmic steps. Step 1. Rewrite the inequality with the larger number on the left, just as in the model. 0.001 greater than 10 to the floor of x. Step 2. Take the base 10 logarithm of both sides. Since 10 is greater than 1, the inequality direction stays the same. Step 3. Replace 0.001 with 10 to the power negative 3. Step 4. Use the logarithm power rule to bring exponents out front. Step 5. Since the logarithm base 10 of 10 is 1, divide both sides by log 10 to isolate the floor of x. Step 6. Apply the floor property. Floor of x less than -3 means x itself is strictly less than -3. To visualize the solution set, consider a number line and highlight all x values self is strictly less than -3. To visualize the solution set, consider a number line and highlight all x values strictly less than -3. We will solve the inequality 10 raised to the floor of 2x is greater than 1000, following the exact logarithmic approach shown in the reference steps. First, display the word example. Now, show the problem in bold orange as 10 to the floor of 2x is greater than 1000. Step 1. Rewrite the inequality using the symmetric property. Swapping left and right keeps the comparison, but flips the order. Show the rule. Display the step title. Then write 1000 less than 10 to the floor of 2x. Step 2. Apply the common logarithm to both sides. Because the base is greater than 1, the inequality direction stays the same. Show the logarithm of inequality rule. Display the step title. Then write log of 1000 is less than log of 10 to the floor of 2x. Step 3. Express 1000 as 10 cubed. Show the power of 10 rule. Display the step title. Then substitute to get log 10 to the third power is less than log 10 to the floor of 2x. Step 4. Use the power rule of logarithms to bring down exponents. Show the power rule. Display the step title. Then write 3 log 10 is less than floor of 2x times log 10, coloring the changed parts. Step 5. Since log of 10 equals 1, we can divide both sides by log 10 to isolate the floor of 2x. Show the fact that log of 10 equals 1. Display the step title. Then show floor of 2x is greater than 3. Step 6. Convert the floor inequality to an inequality without the floor. If the greatest integer of a number is greater than 3, the number itself is at least 4. Show the floor inequality rule. Display the step title. Then write 2x is greater than or equal to 4. Step 7. Isolate x by dividing both sides by 2. Display the step title. Then show x is greater than or equal to 2. We will solve the inequality. 10 to the floor of x is greater than 7. First, show the word example and the problem in orange. Step 1. Use inequality symmetry to rewrite with 7 on the left. Show the rule. Then show the rewritten inequality, 7 less than 10 to the floor of x. Step 2. Apply the common logarithm base 10 to both sides. Because log base 10 is increasing, the inequality direction stays the same. Show the rule. Apply the log to both sides. Step 3. Use the power rule for logarithms to bring the exponent down. Show the rule. Move the exponent, the floor of x, to the front. Step 4. Since log base 10 of 10 equals 1, divide both sides by log 10 to isolate the floor of x. Show the rule. Write the division by log 10. Then simplify to floor of x greater than log 7. Step 5. Evaluate log 7 numerically and use the fact that the floor of x is an integer. Show a floor inequality idea. Compute log 7, about 0.845. Conclude that floor of x must be at least 1. Step 6. Translate floor of x greater than or equal to 1 to x greater of x greater than or equal to 1. We will solve the inequality. The floor of log x is less than or equal to 2 following a clear 3-step algorithm. First, let's display the example and the problem in orange. Step 1. Break down the floor function inequality. We will use the rule, floor of u less than or equal to n if and only if u is less than n plus 1. Applying this to the floor of log x less than or equal to 2, we split into 2 cases. Case 1, the floor of log x is strictly less than 2, which means log x is less than 2. Case 2, the floor of log x equals 2, which means log x is at least 2, but less than 3. Step 2. Combine the range for log x. We use a union rule. From -infinity to a, union with left closed a to b equals -infinity to b. So log x lies in the union of -infinity to 2 and 2 to 3 left closed. This merges to -infinity to 3. Equivalently, log x is less than 3. Step 3. Solve for x and respect the domain. Use the logarithm inequality rule for base 10. Log of x less than y if and only if 0 is less than x and x is less than 10 to the y. With y equal to 3, we get x less than 10 cubed, which is 1,000. And the domain requires x greater than 0. Combining both gives x in the open interval from 0 to 1,000. Final solution set. The set D equals the open interval from 0 to 1,000. Great work! Welcome! In this quick example, we will solve the inequality bracket log x bracket greater than 1 using the floor function rule and a logarithm definition. First, we show the example label and the problem. Step 1. We apply the greatest integer, also called floor inequality rule. If the floor of u is greater than n, then u is at least n plus 1. Here, the floor of log x is greater than 1, so log x is at least 2. Step 2. Use the definition of the common logarithm. If log base 10 of a is at least b, then a is at least 10 to the b. We have log x at least 2, so x is at least 10 squared. Step 3. Evaluate 10 squared. 10 squared equals 100, so x is at least 100. Step 4. State the full solution set. The solution is all x values greater than or equal to 100, which in interval notation is the bracket 100 to positive infinity. Let us also visualize this on a number line. Summary. We used the floor function rule, then converted the inequality with the common logarithm definition, evaluated 10 squared, and wrote the solution set. Final answer x greater than or equal to 100. Final answer x greater than or equal to 100. Welcome! In this lesson, we will find the domains of 4 functions that combine the floor function and square roots. We will use 2 key rules. First, for a square root of u, the inside must be non-negative. Second, if that square root is in the denominator, the inside must be strictly positive. Example, the function is f of x equals the square root of floor of x minus 3. We apply the radical domain rule. Set floor of x minus 3 greater than or equal to 0. That gives floor of x greater than or equal to 3, which implies x is at least 3. Let's mark this on a number line. So the domain is the interval from 3 to infinity, including 3. Example, the function is f of x equals the square root of 3 minus floor of x. Use the same radical rule. Set 3 minus floor of x greater than or equal to 0. So floor of x is at most 3. That means x must be less than 4. Let's show that on a number line. The domain is the interval from negative infinity to 4, not including 4. Example, the function is f of x equals 1 over the square root of floor of x minus 3. Because the root is in the denominator, the inside must be strictly positive. Set floor of x minus 3 greater than 0. That gives floor of x greater than 3, which means floor of x is at least 4, so x is at least 4. We'll mark that on a number line. The domain is from 4 to infinity, including 4. Example, the function is f of x equals 1 over the square root of 3 minus floor of x. Again, the root is in the denominator, so the inside must be positive. Set 3 minus floor of x greater than 0. That gives 3 greater than floor of x. So the floor is less than 3, which means x is less than 3. Let's put that on a number line. The domain is negative infinity to 3, not including 3. Quick challenge. What is the domain of the square root of floor of x plus 1? We will find the largest value of c, such that the inequality holds for all real x. First, let us display the example and the problem statement. Our goal is to bound the right side by something proportional to x squared, so that we can read off the largest possible constant c. Step 1. Analyze the sum of parts. The floor of x plus the fractional part of x always adds back to x. This is the key identity we will use. Quick challenge. Can you see why this is true from the definition of the floor function? Step 2. Determine maximum product conditions. When the sum of plus b is fixed, the product at times b is maximized when it equals b. We apply this idea to the pair x and x minus x. Set them equal to split the sum evenly. This tells us the largest possible value of the product. X times x minus x for a fixed x is at most x squared over 4. That upper bound is all we need. Step 3. Substitute and solve for c. Replace the product on the right by its maximum possible value, x squared over 4. Then we simplify step by step to isolate c. To see why 4 is tight, consider x between 1 and 2, where the floor of x is 1. As x approaches 2 from the left, the ratio forces c to be at most 4, matching our bound. Step 4. Conclude the maximum value. The largest c that works for every real x is 4. Let us highlight the result. Quick summary. We used the identity that the floor plus the fractional part equals x, applied the product maximization principle under a fixed sum, substituted the resulting bound, and solved to find c less than or equal to 4. Try creating your own inequalities and bounding them using this technique. The next topic is properties of the floor and ceiling functions. Take a moment to reflect. Where else can you use the equal split idea to maximize or minimize expressions? Great work! We will solve the inequality, floor of x minus floor of x squared is greater than or equal to 0, following a precise 7-step algorithm, with rule boxes before each step. Step 1. Define the floor function. We write x as n plus p, where n is the integer part and p is the fractional part with p between 0 inclusive and 1 exclusive. Step 2. Substitute and expand the inequality. Replace x by n plus p and expand x squared. We also infer that x must be non-negative for the inequality to hold. Step 3. Factor out the integer part using the property that the floor of an integer plus a number equals the integer plus the floor of that number. Step 4. Analyze non-negative constraints. Since p is at least 0 and n is at least 0, the expression 2np plus p squared is non-negative. Hence its floor is at least 0, and it must be at most n times 1 minus n. This forces n to be 0 or 1. Step 5. Case n equals 0. We substitute n equals 0 and obtain the floor of p squared is 0. That means p ranges from 0 inclusive to 1 exclusive, and x ranges from 0 to 1. Step 6. Case n equals 1. We get the floor of 2p plus p squared is 0, which means 2p plus p squared is at least 0 and less than 1. Completing the square gives p plus 1 squared less than 2, so p is less than square root of 2 minus 1. Therefore, x ranges from 1 to square root of 2. Step 7. Combine the intervals. From the two cases, we get the interval from 0 inclusive to square root of 2 exclusive. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.